Welcome to the deep dive. We take complex topics and, well, we try to make them really clear. Today, we're exploring something pretty fascinating, finding tiny, almost invisible flaws in materials. It sounds straightforward, maybe, but the precision involved is anything but simple. Think about it. How do you reliably spot a microscopic crack? One that could potentially compromise, say, an aircraft wing or a critical part in a machine if you can't even see it. So, our mission today is to give you a really solid overview of the science and the clever applications behind liquid penetrant testing. We'll unpack the special properties these liquids need, how they're carefully put on and taken off, and the ingenious ways we make these tiny flaws practically jump out at you, sometimes with color, sometimes with this like eerie glow. Basically, we want to give you a shortcut to understanding the why behind each step of this really vital process. Okay, so let's start right at the beginning. How does a liquid, any liquid really, even get into a crack that's maybe thinner than a hair? Seems a bit counterintuitive, doesn't it?
It does seem that way at first, but it's really all about harnessing some fundamental physics. I mean, sure, almost any liquid will wet a surface eventually,
Yeah.
but for liquid penetrant testing to work well, it needs liquids with really optimized physical properties. And the main player here is capillarity.
Ah, capillarity. Okay.
Yeah, you probably remember surface tension, right?
Yeah.
That sort of skin a liquid has because its molecules are pulling inwards.
Right.
Well, that and something called the contact angle. Basically, how a drop of liquid behaves when it sits on a surface, that combination dictates everything. If a liquid spreads out completely, wets the surface fully, the contact angle is pretty much zero.
Okay.
If it beads up, like water on wax, the angle is large.
So the crack isn't just sitting there waiting, it's actually pulling the liquid in.
Exactly. That's the capillary action. When the liquid wets the inside of that tiny capillary, the crack, creates this pressure difference. It's quite a significant pressure, actually, drawing the liquid deep inside.
What?
And the dimensions here are just mind-bogglingly small. Think about a crack just half a micrometer wide. That's smaller than one of your red blood cells.
Tiny.
Yeah, incredibly tiny.
Yeah.
But even with a liquid having just moderate surface tension, that minuscule opening can generate huge capillary pressure. We're talking thousands, potentially tens of thousands of pounds per square inch.
That's amazing pressure from such a small feature.
It is. But, and this is crucial, this only works if the liquid wets the surface. If that contact angle is too high, say 90 degrees or more, then there's no wetting.
And no penetration.
No penetration. The whole process stops before it starts.
Okay, so the liquid gets pulled in by this capillary action.
Yeah.
But then how fast does it move? That's where viscosity comes in, right? Its resistance to flow.
Precisely. Viscosity dictates the rate of filling. Now, for most of the defects we're looking for, the actual length of the void is really small.
Huh?
So usually the filling time is just a matter of seconds, unless, of course, the penetrant is, incredibly thick, really viscous.
Which you might think gives you more control, but maybe not.
Well, yeah, high viscosity can cause practical headaches. One big one is drag out, basically, wasting a lot of penetrant because it clings to the surface too much,
Oh, okay.
and it just slows down the penetration time, which isn't great for efficiency in a production environment.
Right. And what about volatility? Does it matter if the liquid evaporates easily? You might think faster drying would be a good thing.
Actually, for the penetrant itself, it's the opposite. Low volatility is really important for several reasons.
Okay.
First, simple economics. Less evaporation means less product lost. Second, safety. Fewer flammable or potentially harmful vapors hanging around the test area. That's a big one.
Definitely.
And third, perhaps most importantly for the test results, low volatility ensures the penetrant's composition stays stable. It doesn't change while it's sitting there dwelling in the cracks.
So its properties remain consistent for removal and fluorescence.
Exactly. You need it to stay put and maintain its integrity until the next step in the process. You don't want key ingredients evaporating off.
That makes perfect sense. It's this careful balance of properties. And I guess that viscosity and volatility also affect how well the excess drains off the surface later.
Absolutely. A thicker, higher viscosity penetrant, for example, might lead to much more drag out, like we mentioned, or you'd need a significantly longer drain time to get the same amount off cleanly. Every detail is engineered.
Okay, this next part sounds really tricky. Once the penetrant has seeped into those tiny cracks, how on earth do you get the excess liquid off the surface without pulling it back out of the cracks you're trying to find? That sounds like a real balancing act.
It absolutely is. This removal step is it's critical. It can genuinely make or break the entire inspection. And yet we've developed several different techniques over the years, each with its own sort of cleverness, but also its own potential pitfalls.
So what are some of those methods?
Well, historically, for certain jobs, people use pretty quick methods like a solvent rinse or maybe vapor degreasing. They clean the surface very thoroughly, but they can be too aggressive if you need really high sensitivity. They might just wash everything out.
Okay, so not ideal for finding the really small stuff.
Generally not. Now, for the common aerosol can penetrants, solvent wipe-off is pretty standard. But this really relies on the skill of the inspector.
How so?
Well, the solvent has to do a few things well. Evaporate quickly, not be too toxic, and dissolve the surface penetrant effectively. But the trick is you have to wipe it just right. You don't want to use too much solvent or rub too hard, or you risk pulling the penetrant out of the flaws.
Right.
And there's a trade-off with safety too. Solvents that are safer, with higher flash points, tend to dry much more slowly, which complicates things. The key is using clean, dry cloths. If your cloths get saturated, you're just smearing penetrant around, not removing it.
Sounds like it requires a delicate touch. Then came water-washable penetrants, I gather. That sounds simpler.
It certainly sounds simpler, and that was the appeal. Just rinse with water and then dry the part. And modern ones are definitely better than the early versions. They're formulated to be a bit more resistant to overwashing.
But still a risk.
But yes, the inherent risk is still there. If you have a complex part with lots of nooks and crannies, an inspector might be tempted to use a really strong water spray to get it clean.
Huh?
And if they do that too vigorously, it's still quite possible to wash the penetrant right out of the shallow defects, making the final indications dim or even invisible.
Okay, so to get around that overwashing problem and maybe push the sensitivity higher, the industry came up with post-emulsifiable penetrants.
Exactly. The first main type used lipophilic emulsifiers.
Mm-hmm.
Lipo meaning oil-loving.
Right.
So here, you'd apply the penetrant, let it dwell, and then apply this separate emulsifier liquid. It would diffuse into the penetrant layer sitting on the surface, making that layer washable with water.
So it targets just the surface layer.
That was the idea.
Yeah.
And for a long time, this was the go-to method for high-sensitivity inspections. But it had significant drawbacks.
Ah, okay. What were they?
Well, these emulsifiers were often quite viscous, oily themselves, so you used a lot, leading to high consumption and, frankly, quite a bit of oily wastewater pollution.
Environmental issue, too.
Definitely. And, critically, if you left the emulsifier on for too long, or if conditions weren't quite right, it could actually start to diffuse down into the cracks.
Oh, contaminating the penetrant you want to keep.
Precisely. It mixes with the penetrant trapped in the flaw, diluting it, making the final indication much fainter than it should be. This potential for contamination was a major issue, and it's why lipophilic systems are largely becoming obsolete now.
That makes sense. You solve one problem but create another potentially worse one. So that brings us to the better alternative, hydrophilic emulsifiers.
Yes, these were a real game changer. Hydro, meaning water-loving. These are different. They're typically detergents or dispersants dissolved in water.
So how do they work differently?
Instead of diffusing into the penetrant, they work by preferentially wetting the metal surface underneath the penetrant layer. They sort of gently lift or peel the excess penetrant off the surface.
Like getting underneath it.
Kind of, yeah. And they break it up into tiny droplets that get dispersed in the water and don't tend to redeposit onto the part.
And the big advantage?
The huge advantage is much brighter indications, because the emulsifier doesn't really mix with or contaminate the penetrant that's trapped down in the flaws.
Yeah.
What's in the crack stays pure.
Nice.
Plus, these solutions are usually thin, almost like water themselves, so you don't get much drag-out waste. They're pretty efficient.
Any other benefits?
Well, they can tolerate a certain amount of penetrant contamination in the tank before they stop working effectively. And you can apply them in different ways, spraying, dipping, even foaming sometimes.
And you mentioned something about pre-rinsing as an efficiency tip.
Oh, yes. This is a really smart technique, especially with hydrophilic systems. Before you even apply the emulsifier, you give the part a quick rinse with plain water.
What does that do?
It washes away a lot of the loose, gross surface penetrant, sometimes up to 90% of it. This massively reduces the amount of oily penetrant that gets into your emulsifier tank.
Ah, so the tank lasts much longer.
Significantly longer. And it drastically cuts down on the oily waste you have to treat or dispose of. It's great for both cost and the environment. A real win-win.
That's clever. It all comes back to being precise and, well, not overdoing it. Which reminds me of that rule you mentioned.
Ah, yes, the golden rule of removal. And it really applies across the board, no matter the method. Do just enough to clean excess fluorescence off the surface. Doing the job more thoroughly will not help, but can surely hurt.
That really sums up the challenge, doesn't it? Precision, not brute force. Okay, so we've navigated getting the liquid in, letting it dwell, and then carefully getting the excess off. Now, how does all this careful work actually help us see the defects? This is where we make the invisible visible, right?
Exactly. This is the payoff. Let's compare the two main types.
Hmm.
First, you have non-fluorescent, or what most people call visible liquid penetrants.
The red dye ones usually.
Typically red, yes, because they rely purely on visual contrast. You use a strong color difference between the indication and the background. That's why you almost always use them with a bright white developer, dark red lines on a white surface. Pretty clear.
Makes sense. But are they good for finding really small things?
That's their limitation. On a standard test panel, for instance, you might clearly see cracks that are, say, 50 micrometers wide. But when you get down to maybe 30 micrometers, the red lines start looking faint, maybe a bit spotty, pale pink almost.
Uh-huh.
And below that, trying to find 20 or 10 micrometer cracks with visible penetrant, it's generally impossible. There just isn't enough dye concentrated in such a tiny volume to create a visible signal our eyes can pick up against the background.
And there's actual physics behind that limitation, isn't there? Something called the Beer-Lambert law.
That's right. It's a fundamental law in optics. For these visible colored penetrants, the amount of light the dye absorbs, which is what gives it the color we see, depends on a few things.
Yeah.
The dye's inherent ability to absorb light, its concentration, and critically, the thickness of the layer the light is passing through.
Ah, the thickness.
Yes. And this law basically tells us that in extremely thin films, like the tiny amount of penetrant seepage from a microscopic crack, the light absorption drops off incredibly fast. Below a certain thickness, the indication just becomes effectively transparent. Our eyes simply can't perceive that faint color. It sets a real physical limit on their sensitivity.
Which naturally leads us to fluorescent liquid penetrants for finding those really, really tiny flaws. They work differently.
Completely differently and vastly more sensitively. These penetrants don't just absorb visible light, they absorb invisible near ultraviolet radiation, usually called UVA or black light.
Okay.
And then, crucially, they convert that UV energy and re-emit it as visible light, typically a bright yellow-green glow.
So they make their own light, essentially.
In a way, yes. The Beer-Lambert law still applies to how they absorb the incoming UV light. But they blow past the limitations of visible dyes for three main reasons.
Okay, what are they?
One, the fluorescent dyes themselves are generally much more efficient at absorbing the incoming energy compared to visible dyes absorbing invisible light. Two, you get a much more favorable visual situation. A bright glowing line against a dark background, which our eyes are naturally very sensitive to detecting.
Light on dark is easier to see than dark on white sometimes.
Much easier, especially for faint signals. And the third reason, which is maybe the most important, is the role of the developer. The developer doesn't just draw the penetrant out. It interacts with the emitted fluorescent light through light scattering in a way that dramatically boosts the apparent brightness.
How much brighter?
It can be almost an order of magnitude, like 10 times brighter. This combined effect is what lets fluorescent penetrants find discontinuities that are far, far smaller than anything a visible penetrant could ever reveal.
Okay, that developer part sounds like real magic. You said it's not just a passive background, but an active magnifier. How does it take that, maybe faint seepage and turn it into something clear?
It is pretty ingenious, because you're right, without a developer, even a fluorescent indication might just be a very thin, faint line of liquid, maybe hard to spot.
Yeah.
The developer is the key to making it pop.
So how does it work? Let's talk about dry developers. You said they're like fine powders.
Exactly. Incredibly fine, fluffy particles, often less than a micrometer in size, some even smaller.
Yeah.
Their main job is to provide a better capillary path than the original crack.
Better how?
They essentially act like millions of tiny wicks. They literally suck the trapped penetrant out of the flaw by capillary action. But here's the clever part. As they draw it out, they also allow it to spread laterally across the surface particles.
So it widens the indication.
Considerably.
Yeah.
An indication might end up looking 50 or even 100 times wider than the actual crack opening. It's a simple physical magnification effect.
Mm-hmm.
And their tiny particle size is key. It helps them stick to the surface and effectively bridge over the flaw opening to start that wicking action.
That makes sense. But they don't work for visible penetrants.
No, because they're usually white or off-white powders themselves.
Mm.
They don't provide that necessary dark indication on white background contrast needed for visible dyes. They're strictly for fluorescent.
Okay, what other types of developers are there?
Well, there are aqueous particulate developers. These are powders suspended in water. You apply them, let the water evaporate, and you're left with a white film. Good for both visible and fluorescent, easy for large parts.
Yeah.
Then you have solvent-based particulate developers. These are often seen as the most sensitive, especially for portable kits like spray cans. The solvent carrier helps to draw the penetrant out very quickly before it evaporates, leaving the particles and the indication. They provide contrast for visible and scatter light for fluorescent. But they do come with more health and fire hazard concerns.
Okay.
And finally, there are water-soluble developers. These actually dissolve in water, you apply the solution, dry it, and it leaves a film. Can be easier to rinse off later, but sometimes the film isn't as good at scattering light or providing capillary action as the particulate types. Generally not preferred for visible penetrants.
You keep mentioning light scattering for fluorescent testing. You said that's a really critical point, more than just magnification.
Oh, absolutely critical. It's maybe the biggest single reason, besides the fluorescence itself, why these systems are so sensitive. It addresses a fundamental problem. It's called the light trap effect. When the fluorescent dye emits its visible light inside that thin layer of penetrant, a huge chunk of that light, maybe as much as 87.5%, gets trapped inside by total internal reflection.
Like light hitting the surface from inside at a shallow angle and just bouncing back in?
Exactly. It can't escape to reach the inspector's eye. It's just reflecting internally. A lot of the light generated is wasted, essentially.
So the developer breaks that trap.
Precisely. The developer particles coating the penetrant seepage provide countless tiny, randomly oriented surfaces. When the trapped light hits these particles, it reflects and refracts in all directions. This allows nearly all of that previously trapped light to escape the film and travel towards the inspector.
And that's where the huge brightness increase comes from.
That's where that potential 8-fold or even more increase in apparent brightness comes from. It's unlocking the trapped light. But wait, there's more.
Oh.
The developer particles also play another scattering role. They scatter the incoming ultraviolet radiation throughout the penetrant seepage layer.
Why is that important?
Because in these microscopically thin seepages, the UV light might just pass straight through without much being absorbed on the first pass. By scattering the UV within the layer, the developer ensures that pretty much all the UV energy gets a chance to be absorbed by the dye molecules, even in a tiny amount of penetrant. This maximizes the amount of visible light that gets generated in the first place, so it boosts emission and escape.
Wow. That's really clever. It's working on both ends, maximizing the light produced and maximizing the light that gets out.
Exactly. It's a multifaceted enhancement.
Okay, so we've got the science down, the process refined, the developer doing its magic. But it all comes down to the human element, doesn't it? All this work creates an indication, but you, the inspector, still have to see it, interpret it correctly. The eye is the final sensor.
Absolutely. It's a vital link in the chain and, yeah, sometimes overlooked in the focus on materials and chemistry. Let's think about visible indications first.
Now, red on white.
Right. Ideally, you want that sharp, dark red line against a really uniform snow-white developer background for maximum contrast. Quick tip. Sometimes viewing those indications under green light or even through green-tinted glasses can make the red appear almost black, enhancing the contrast even further for some eyes.
Interesting.
And inspector skill is huge, especially, as we touched on, when applying those solvent-based developers from spray cans. It's an art. You need a thin, even coat. Let it dry just enough. You absolutely cannot let the surface get wet or runny with the developer.
Why not?
Because the solvent can then dissolve the penetrant indication and make it bleed or spread unnaturally. And critically, you have to stop spraying before the developer coat gets thick and completely opaque white.
Because it would hide the indication.
It can literally mask or obscure very fine indications if it's too thick. The rule of thumb is you spray just enough until the original surface texture and color are almost hidden, but not quite totally obliterated. Thin and uniform is key.
Got it. And for fluorescent indications, what are the critical viewing factors?
Two main things: the right light and the right environment. You absolutely must view fluorescent indications under the specified UVA radiation, usually centered around 365 nanometers. And it has to be done in a darkened area.
Why so dark?
Because any significant amount of ambient visible light, room light, sunlight will completely wash out the contrast. Your eyes adapt to the brighter visible light, and the faint fluorescent glow just disappears against it. Standards usually specify very low levels of background white light, maybe only 1 or 2 foot candles.
So dedicated inspection booths are essential.
Absolutely essential for reliable fluorescent inspection. Trying to do it in a well-lit shop is just asking for missed flaws. The required UV intensity would have to be astronomically high to compete with bright ambient light, which isn't practical or safe.
And what about the inspector's actual eyesight?
Hugely important. Basic visual acuity, of course. Making sure your eyes have properly adapted to the darkness before you start inspecting that takes several minutes. But also, specific conditions can impact things, especially with fluorescence.
Like what?
Well, cataracts are a big one. They can obviously blur vision, but they also tend to yellow the lens of the eye over time,
And that matters because
because that yellowing preferentially absorbs blue and violet light. Since some of the fluorescent glow is in that shorter wavelength range, a yellowed lens can filter it out, making indications appear dimmer, maybe more reddish, and reducing the eye's ability to resolve fine details.
Wow. And what about after cataract surgery?
That can introduce a different effect. Modern replacement lenses are crystal clear. So suddenly, the inspector might perceive the UV lamp itself, which always emits a little bit of visible violet light, as intensely violet or blue. This intense lamp color can sometimes visually overwhelm or wash out very faint fluorescent indications that they might have seen before surgery.
That's incredible. So eyesight isn't just about sharpness. It's about color perception and adaptation in this specific context.
Exactly. And while these aren't properties of the penetrant materials themselves, understanding accounting for human vision performance is absolutely critical for planning tests and evaluating results reliably. The whole system includes the inspector's eyes.
It really drives home that this whole process, from start to finish, is this intricate dance between material science, clever chemistry, precise procedure, and ultimately human perception. So just to recap our journey here, we started with the microscopic forces like capillarity, pulling liquids into impossibly small cracks. We navigated the really delicate steps of removing excess penetrant without disturbing the clues. We explored the science of color and light, why red dye works, why fluorescence is so much more sensitive. We saw the frankly amazing tricks developers use to magnify and brighten those signals. And finally, we landed on how crucial the human inspector's viewing conditions and eyesight are. It's quite a blend.
It really is. And if you think about the bigger picture, liquid penetrant testing is just a fantastic example of how really understanding fundamental scientific principles, things like surface tension, viscosity, light absorption, fluorescence, scattering, how that deep understanding allows us to create incredibly effective practical tools for ensuring safety and quality in the real world. It's applied science doing exactly what it should.
So what does this all mean for you listening? Well, maybe next time you look at a bridge or an airplane or even just a complex metal part, you might think about that hidden, invisible world of potential flaws lurking within. And you'll have a better appreciation for the specialized liquids and clever techniques designed specifically to bring those hidden dangers to light. It's a testament to human ingenuity, really. And maybe here's a final thought to leave you with. Consider that silent partnership we saw today between the basic inherent properties of matter and our own ingenious designs to manipulate them. How much more are we overlooking, right there in plain sight, just waiting for the right kind of deep dive to reveal its secrets?